Okay, so in this video, we're going to go over how to construct confidence intervals for sample means. We're going to assume, now that we know, remember that for sample sizes of at least 30, the distribution of sample means follows a normal distribution where the mean of the sample means distribution is the same as a population mean, but the standard deviation is not. It's the standard of the population, but divided by the root of the sample size. N has to be more than 30. So in this picture, the standard deviation is this value. So I'm going to start working with confidence level 90% just to make things clear, to make things like a wrap our brains around this. So imagine that we can say with probability 90%, our point estimate, this is just our sample mean, is between the mean minus this value and the mean plus that value, where the ZZ is a z-score that traps the middle 90% of the standard normal curve. So what that means is that under the standard normal curve, you have two values, symmetric right around the mean. Sorry, the mean is 0 on the standard normal curve. So if you remember, this is the one that has mean 0, standard deviation 1. And you can find the two values, negative ZZ and ZZ. I'm calling it ZZ in general, but I'm going to use 90, so this would be really the Z90. So these are the two values that trap the middle 90% in here. Okay. So if you find those two values, then converting to X scores, right, under my standard normal curve, if you have the mean of your sample means and you add that plus the z-score times the standard deviation, that will be the equivalent value here, and then you do the mu minus the z-score times the standard deviation of the sample means, and that will give you the value here. That will give you the two values that trap the middle 90% over here. So this is how we convert, knowing that the middle 90% of the standard normal curves translates to the middle 90% under this curve. Okay, so this is all I'm saying right there. Now, with 90% confidence, because I'm using 90%, right, in the area, with 90% confidence, that's where the word confidence comes from. We grab that instead of probability 90%, we become 90% confident. We say that the sample mean, I'm going to repeat the picture here. So I have this, I have this value over here, I have this value over here, and I'm saying that with 90% confidence, my sample mean is going to land here. Right? This sample mean lives under this, is a value under this curve. There's 10% chance that it falls over here, and 90% chance that it lands in here. So that's how I interpret this statement. Now, this inequality here can be rewritten into inequalities, right? I can think of it like this inequality on the left becomes this one, and this inequality on the right becomes this one. Now, solving each one of these for the mean becomes very simple. The mean, you add that over here, and it becomes like that. You subtract the ZZ in this case, and it looks like that. But now putting these two inequalities that I got, very simple ones, together as a nested inequality, I can think of it, this is an inequality now centered around the mean, right? From here I can write it like the mean is a value less than x bar plus the ZC sigma x, and now using this one, greater than x bar minus the ZZ sigma x, sorry, space. So this tells you that you can write it really like that. Right? The mean is between the x bar minus the z sigma, and x bar plus the ZZ sigma x. And all this was with 90% confidence. So now we're saying with 90% confidence, the real mean, or the population mean, lies between these two values. So this is what is called a 90% confidence interval. Okay, so the confidence interval is something centered at the, at the, at the point estimate. We add and subtract this value. Well, that value is what we're going to call the margin of error. Right? The margin of error is this number. So it's just the ZZ times the sigma that we're using for the confidence. The margin of error can be interpreted as the maximum distance between the point estimate and the population mean under the confidence that we're using, right? And of course, if you just call this the margin of error, then this looks very simple, like x bar minus the margin of error and x bar plus the margin of error. Okay, so where do we go from here? Let's do an example. So say I have 40 light bulbs, so my sample is 40, my sample size is 40. Give a mean lifetime of 960 hours. So as we go through this, I'm seeing that my n is 40, so it's more than 30. We need that. And has a mean lifetime of 960, so that's my x hat. X bar is 960. From previous data over the years, it is estimated that the standard deviation of all light bulbs from this manufacturer's 24 hours, that's going to be our sigma, or the population, right? So construct a 90% confidence interval for the mean lifetime for the light bulbs. So I need to find the ZZ. The ZZ is the 90%, the value that leaves in the middle 90% of the value. Now here, you have to be very careful. This is under the standard normal curve. I'm looking for what value leaves the middle 90%. After a while, this becomes automatic, but we have to think about it at the beginning. I want the 90% in the middle, which means there is 10% between these two tails. That leaves me 5% over here and 5% over there. Now, the way we can calculate the inverse value, so the z-scores in this case, it's always areas to the left. So I'm going to use the calculator ClassCalc. So I'm going to use, if I use this one to find this value, I'm doing the inverse normal of 0.5. If I want to find this value, it's not important. I know it's symmetric, it's just a positive value. It would be the inverse normal of 95 because I want to find, I'm going to have to put the area of all that to the left. Okay, just be careful with that. So I'm going to grab the ClassCalc calculator, and I'm going to type statistics. I need to switch calculator to the graphing calculator. Now statistics, I get the big thing. I think I'm not seeing that. To graph the graphing calculator. There we are. Now I can press statistics. Now I'm going to press this test button right here. Oh no, sorry. I just need to type. I forgot what I was doing. I'm getting ahead of myself. So I need to find the distribution plots, the normal distribution, and I want to use the one with mean 0, standard deviation 1, and I want to find the inverse. So I can close that, and I go against that distribution, and I'm using the inverse CDF. And I want the point, I'm going to use 0.95. So it's 1.64, I'm going to use 645. Okay. Let me go back. So I use this calculator to find this, so my ZZ is 1.645. That's the Z value that leaves the middle 90%. Now how to find the E? Well, the E, if you remember from before, was just the ZZ times the standard deviation of the sample mean. So I need to find, this would be, E would be ZZ times sigma X. So it really is the 1.645 times my standard deviation, which is 24, but divided by the root of the sample size, which is 40. Okay, so I need to do 1.645 times 24 divided by the square root of 40. So I get 6.24. So there we go. This is the margin of error, and I construct the interval. How do you construct the interval? It's just to be the x bar minus the e and the x bar plus the e. So pretty simple. My x bar was 960. I can grab it from right here. So I can add it very easy. It's 966.24. And maybe I don't want to do the other one, so I can do very simple here, 960 minus the 6.24. And that would be 953.76. So I can report it like that, like two values, or if you're asked to report it back as an interval, it will be the interval 953.76, comma, 966.24. In fact, so we need to know how to do this with the formulas, but the calculator can do the whole thing for us. So I'm going to show you how to do that. So in the button where I had stat, if I scroll here and really click where it says test, and I'm using the button in this level that says test, it's the last one, then I'm really not using the test right now. I'm using this button right here that says z interval, okay, at this level. You press the z interval, look what it asks you, sorry, the menu's right here. Oh, let me erase everything. Let me go over. So I go stat, test, z interval. Why z? Because we're using the z values, the z curve, the standard normal curve. Okay. The sigma that we're using, the first thing it asks you is the sigma, and that was 24. Is that what I used over here? Yeah. And then the x hat is what I got from my sample. That's the 960. Now the n, the sample size we're using, is 40. And the last thing I ask you is for the confidence level, we put it as a decimal, so 0.9. And there you go. It gave us directly the 953 at this level, 75, and the 966.24. Yeah, so these are numbers the calculator is giving us, 953.76, rounds to this, right? Sorry, I can erase that. And 966.24, this value. And it reports right here, this number, the ME, is a margin of error, the number we got from here. So the calculator gives us directly this, so we can use it, but there's going to be some instances where you still need to jump into the formula, as we'll do in a minute. So before I get to that, a little note on the standard deviation. The examples we're using right now, we're assuming we have a prior estimate of the published standard deviation. This might not be the case. We might not have an estimate of the population one. If we have a sample size 30, it's not a big deal. We can use the sample standard deviation. We can always calculate it from there and use that one as an estimate for the standard deviation of the population. We're going to be working with cases later when we have small samples, so less than 30, and how to do that. We'll talk about that in a later class. So in this case, we're assuming that we know the population standard deviation, or they have a good estimate for it using either the sample size, a sample standard deviation if we have a big sample, or a prior estimate. Let me just do one short last example. So I'm going to use an example because in this one you'll see that the calculator would not solve us a problem. So a consumer agency wants to test a certain model of batteries to estimate their mean lifetime. They want to report a 95% confidence interval with a margin of error of 2 hours. What size should be the sample? We have the prior data that gives us standard deviation of the population to be 7.5. So this is a problem where it's a little bit backwards. I'm going to grab this from here. Okay. Look, I'm going to grab this information here. So what we know is that the margin of error is the z-score that I'm going to find in a minute times the population standard deviation divided by the root of the sample size. Right? In this example, what I don't know is the sample size. So what I need to do is solve for it. I am going to know the ZZ because the ZZ comes, this value comes from the confidence level. I do know the standard deviation that's given right here. I'm given that they want the margin of error to be 2 hours, so I have a target for the margin of error. So the only thing I don't know is the n. So very simple, we solve for n, right? If you multiply by the root of n, this looks like this. The root of n equals zz sigma divided by e. And then I have a square root, so the n is going to be that quantity squared. And there's no other way to do this. You're going to have to solve this problem using these formulas. So even though technology can help us find directly the interval directly, it would not find the sample size. So we still need to find, for example, here, what is the ZZ for a 95% confidence. So remember that for a 95% confidence, what I'm looking for is what are the z-scores that trap the middle 95%. And using the same logic, if there's 95% in the middle, there's 2.5 on each tail. So to find that value, I erased everything, I think, so I had to do it again. So I'm going to do stat, distribution, normal distribution with 0, 1. And I want the inverse normal. So inverse CDF of point, I either do E0 to 5, okay, or I do the 975. So if I put here 975, I get the same value but positive. So I'm going to round that to 196. So my n is 1.96. The sigma, I have it. It's 7.5. And the margin of error is given to be 2. And then I square that. So my sample size, I'm going to do it right here. Oops, sorry, I typed something up here that I wanted. So I just have to do 1.96 times 7.5 divided by 2, and then I'm going to square that quantity, and I get a sample size of 54. It's over 54, so you have to go back up to 55. Okay, always round up. Okay, so this is how you would need to solve a problem if you need to find a sample size given a targeted margin of error.